In this lesson, we're going to look at properties of aqueous solutions and define a solution and describe its parts. We're going to describe how an aqueous solution is formed from both ionic compounds and molecular compounds, and describe the differences among strong, weak, and non-electrolytes. First, we want to understand the components of a solution. In this case, we're looking at a solution in the liquid phase, but we'll soon see that solutions can happen in any combination of phases. A solution contains a solute, which is present in a smaller amount, and a solvent, which is present in the larger amount. Together, the solute and solvent form a solution. Many of the solutions we will look at are called aqueous solution because they have water as the solvent. When solutes dissolve in water, they can behave differently. Some species will dissociate completely, and those are known as strong electrolytes. When they dissociate completely, what we mean is that each unit of the compound breaks apart into ions. For example, if I put KCl in water, if I looked in the water, what I would actually see are potassium ions and chloride ions. I would not see any units of KCl together in one unit. It would all be present as the separate ions. Notice that we use the abbreviation S in the equation to indicate a solid, and we use the AQ to represent aqueous, meaning it's dissolved in water. Dissociate simply means to break apart into its components. Note that dissociate and dissolve are two different things. A species can dissolve in water, but that doesn't necessarily mean it will dissociate into its ions. In this case, KCl both dissociates and dissolves. Note that ions are charged particles, so we see that with K plus and Cl minus explicitly showing a charge. And the arrow pointing in one direction shows us that the reaction goes completely to the right. So all of the KCl breaks up into the K plus and Cl minus ions. As a result, we get our solution with only ions and no units of KCl. And this creates a solution that has a high conductivity. Note that pure water is actually a very poor conductor of electricity. However, whenever there's lightning, you're always told to get out of the pool or get out of water. And that's because most of the water around us is not considered high purity. There are other species in the water that allow the water to become a good conductor of electricity because it's a solution and not pure water. Weak electrolytes dissociate partially in water. Again, dissociate and dissolve are two different things. So we see a small percentage of the molecules break apart into ions. Acetic acid is an excellent example of a weak electrolyte. When we look at acetic acid after being added to water, what we see is that a few of those molecules have broken up to form ions, but most of the substance is present in the molecular form, so it's still present as those acetic acid molecules. In this case, we show the equilibrium arrow, and this is pointing in both directions. And what this tells us is that the reaction is actually going in the forward and reverse directions. I wanted to draw your attention to the equilibrium arrow, and we will discuss it further in a later lesson. We use the equilibrium arrow when we have a reaction that can go in either the forward or the reverse directions. The equilibrium arrow is used whenever we have weak electrolytes. So it's a way to indicate that something is actually a weak electrolyte when we use the equilibrium arrow. Notice that an acetic acid solution has a very low conductivity. We have some ions that are able to carry the charge within the solution, but not a high number as we would have in a strong electrolyte. Non-electrolytes do not dissociate in water. Ethanol, shown here as initially as a liquid and then as an aqueous solution, is dissolved in water, but it did not dissociate in water. So the molecules remain intact and do not break apart. If we zoomed into it at a molecular level, we would see all ethanol molecules and no pieces of ethanol molecules from dissociation. We only have molecules in the solution, we don't have any ions, and as a result, it is a non-conductor of electricity because there are no ions present, only the molecules. This table shows how we can divide substances as strong, weak, or non-electrolytes. At this point, we have talked about ionic compounds, and ionic compounds are strong electrolytes. We have also talked about molecular compounds, which are considered to be non-electrolytes. We will also see strong acids and strong bases are considered strong electrolytes, and weak acids and weak bases are considered weak electrolytes. The most common example of a weak acid that we will see are our carboxylic acids that we saw in organic functional groups. All carboxylic acids are weak acids. We will explore other options for acids and bases in a future lesson. For now, you should focus on the ionic compounds, weak acids from carboxylic acids, and the molecular compounds.